Welcome to Space Dreams documentary, where Sirius white dwarf shadow, ancient lore and hidden physics unfold. Tonight, one brilliant point widens into system history and physics, too deep for first sight. Sirius seems sovereign and single, yet its brilliance begins inside a binary system with a companion. It rules the night not by power alone, but by luminosity combined with extraordinary nearness. Before Sirius B appeared, Sirius A already wobbled quietly, proving gravity was pulling from the dark. So the familiar star became a measurement problem, where motion revealed structure long before vision did. Beside radiant Sirius moves Sirius B, the compressed remnant of a star that already died. From Earth, it looks fixed, yet both stars trace a changing orbit across roughly 50 years. The dimmer star holds the deeper shock, smaller than Earth, yet carrying nearly solar mass. Sirius B endures as crushed matter, where ordinary intuition fails before impossible density and weight. What resists collapse here is not fusion, but quantum pressure, holding stellar remains against gravity. In that silent remnant, the laws beneath starlight appear more clearly than brightness ever could. Sirius B becomes prophecy when it previews the dense white dwarf future awaiting sun-like stars. Before physics explained Sirius returning, light-shaped omens flood calendars and the feared dog days. Those beliefs were structured attention, because regular brilliance made Sirius a clock warning and marker. Again and again, the sky rewarded repetition, turning seasonal return into memory, order, and expectation. Sirius keeps teaching that first attention misleads, whether distortion comes from glare, myth, or instinct. Sirius B reached death first, evolving faster, shedding its layers, and leaving Sirius A beside ruins. Now, Sirius reads as an archive storing evolution, orbital mechanics, remnant physics, and human meaning. Its brightest lesson is depth the nearer Sirius seems. To understanding, the more structure appears. Please like and subscribe. Thank you for listening. And now the single star begins to divide. The brightest star in the night sky is not the star most people think they are looking at. It appears simple. It appears singular. It appears like the most obvious object in the winter sky, a white-blue point burning above the horizon with such intensity that it seems to explain itself. But Sirius has always been larger than its appearance. The familiar story is that it is bright because it is powerful, because it stands out, because nature placed one especially radiant beacon above Earth and left it there for every civilization to notice. The real story begins when that explanation stops being enough. Brightness is not identity. Visibility is not understanding. And the star that generations treat as a fixed point of clarity turns out to be a layered system of motion, mass, death, survival, and hidden companionship. Sirius is bright, yes. But what matters is not the brightness itself. What matters is the structure beneath it. To the naked eye, Sirius dominates because it seems close to human scale. It flashes through atmospheric turbulence in cold night air. It hangs low for many observers, flickering in unstable colors, near the horizon, almost alive with agitation. It is easy to mistake this familiarity for simplicity. Easy to assume that what is so visible must also be transparent. Yet astronomy repeatedly advances by destroying exactly that assumption. The heavens do not become clearer when something becomes more famous. Often the reverse happens. Repetition dulls strangeness. Recognition conceals complexity. Sirius is one of the oldest known stars in human culture, precisely because it is impossible to ignore, But its constant presence hides the fact that it is not merely a bright object. It is a nearby stellar system, roughly 6 light-years from Earth, anchored by Sirius A, a hot main-sequence star about twice the mass of the Sun, and more than 20 times as luminous, whose raw output and relative proximity combine to make it shine with unmatched intensity in Earth's night sky. That sounds like the answer. It is only the first layer, because even that description creates the wrong mental picture. It suggests a solitary giant whose brilliance explains everything. It suggests that the system's importance begins and ends with radiance. It suggests that Sirius is fundamentally about spectacle. It is not. The story on the surface is smaller than the story underneath. Sirius matters because it stands at the intersection of several truths people rarely hold in mind at once. It is ancient in human memory. It is modern in scientific significance. It is visually immediate, yet physically extreme. It is a symbol in myth and a laboratory in astrophysics. And even at the level of basic perception, it misleads. Human eyes see one star. Gravitational reality says otherwise. The obvious explanation is not the real one. The system that appears as one point contains more than one fate. One member still burns with ordinary stellar life. The other is the remnant of a star that has already died. That hidden second object will change everything. But even before it appears, Sirius already forces a deeper question. Why does one star command so much attention across history, geography, and scientific time? Part of the answer is position. Part is physics. Part is accident. Sirius belongs to Canis Major, the greater dog, and rises in seasons that gave it immense practical and symbolic weight for ancient observers. It becomes not just a light in the sky, but a marker in time, a signal attached to heat harvest omen, kingship, danger, and renewal. That does not happen because humans are irrational. It happens because repeated celestial patterns become tools long before they become equations. A bright star that returns with seasonal regularity enters calendars before it enters spectroscopy. It enters religion before it enters orbital mechanics. It enters civilization before it enters theory. Sirius is a reminder that human beings often detect importance before they understand cause. They feel the weight of a pattern first. Only much later do they uncover the machinery beneath it. That is where the modern story begins to sharpen. Because once observation becomes measurement, the star ceases to be merely impressive and becomes diagnostic. Its light can be separated. Its motion can be tracked. Its distance can be calculated. Its mass can be inferred. And every one of those steps makes the simple picture harder to sustain. The brightest star in the sky should have been easy to classify. Instead, Sirius keeps widening. It becomes one of the first stars whose distance is measured with real confidence. It becomes a benchmark of stellar luminosity. It becomes evidence that the night sky is not composed of decorative points fixed to a distant shell, but of individual physical suns scattered across depth so immense that even the nearest among them are separated from Earth by trillions of miles. This is where the scale begins to shift. Sirius is not bright in the way a nearby lamp is bright. It is bright across interstellar distance. Its light spends 8.6 years crossing the void to reach human eyes. Every glance at Sirius is an encounter with delayed reality, a message launched when Earth itself was different by nearly a decade. That still sounds manageable until scale becomes visible. Light moving at nearly 300,000 kilometers per second takes more than 8 years to make the trip. Human intuition has no native grip on that kind of separation. The star feels immediate. The physics says otherwise. And that tension between felt nearness and actual distance is the first key to the entire system. Sirius always seems closer than it is, simpler than it is, more complete than it is. That is why it becomes such a powerful entry point into the larger truth of astronomy. The universe does not hide only in the faint and remote. Sometimes it hides in the familiar. Sometimes the object seen for thousands of years turns out to be stranger than the newly discovered one. Sirius is not just the brightest star in the sky. It is the first false answer. It is the point where visibility tempts confidence and confidence begins to break. Because once astronomers stop asking why Sirius is bright and start asking why Sirius moves the way it does, the star that looked most obvious begins revealing that it is not one straightforward beacon at all. It is a system with a second presence buried beside the first. And the brightest light in the sky is about to lead directly to something almost impossible to imagine. The first lie Sirius tells is that brightness is a complete explanation. It is not. Brightness feels decisive because human perception is built to trust what overwhelms it, and Sirius overwhelms almost every other star in the sky. It cuts through winter darkness with such confidence that it seems to settle the question before the question is even asked. This must be one of the most powerful stars near Earth. This must be a simple case of overwhelming luminosity. This must be the whole story. But apparent brightness is not a verdict on what a star is. It is a composite effect, a negotiation between intrinsic power distance and geometry between what the object emits and where the observer happens to stand. The answer seems clear until the scale becomes visible. Sirius is indeed luminous, far more luminous than the Sun, with Sirius A radiating roughly 25 times the Sun's output. Yet, luminosity alone does not explain its dominance in Earth's sky, because the sky is not a ranking of raw power. It is a ranking of what reaches human eyes from a specific location inside the galaxy. That difference matters. It matters because it breaks the intuitive shortcut people take, not only with Sirius, but with almost everything they see above them. The brightest thing is assumed to be the biggest story. The most visible object is assumed to reveal its own cause. But astronomy keeps exposing the weakness of that habit. Some stars are vastly more powerful than Sirius and still appear dim because they are far away. Some are physically enormous and visually modest because distance reduces their authority to a point barely perceptible to the eye. Sirius dominates, not because it is the largest or hottest star in any absolute cosmic sense, but because it occupies a rare intersection, highly luminous, relatively nearby, and positioned in a way that makes its light impossible for earthbound observers to ignore. This only looks simple from a distance. The deeper truth is that the night sky is a map distorted by perspective. Human beings do not see the universe as it is. They see it from one moving planet through one atmosphere, from one local angle inside one spiral galaxy. Every brightest or largest looking object is partly a fact about the cosmos and partly a fact about the observer. Sirius reveals that distortion with unusual force because it feels so absolute while being so contingent. Shift Earth elsewhere in the Milky Way and the hierarchy changes. Shift Sirius farther away and its rule ends. Shift the observer out of the atmosphere and some of its flickering drama disappears. The star does not merely shine. It performs through conditions. And that performance has shaped how humans interpret it for millennia. Seen low in the sky for many northern observers, Sirius often flashes with unstable color because its light is forced through thicker layers of turbulent air. It can seem to pulse red, blue, white, even greenish for brief instants, not because the star itself is chaotically changing color, but because Earth's atmosphere bends and disturbs its light before the eye receives it. Once again, the surface story fails. The visible behavior is real. The obvious explanation is not. This pattern repeats. At almost every level, Sirius invites a naive reading first and then punishes it. That is what makes it such a powerful object in the history of science. A bright star is expected to confirm old habits of thought. Instead, Sirius undermines them. It teaches that radiance can conceal mechanism, that familiarity can obscure structure, that perception can describe an effect while missing the cause. Even the simplest question, why is Sirius the brightest star in the night sky, turns out to require a chain of reasoning that moves far beyond ordinary seeing. Its spectral type temperature, luminosity and mass place Sirius A among the hotter and more energetic main sequence stars near the Sun, with a surface temperature close to 10,000 Kelvin and a blue-white character very different from the Sun's calmer yellow-white appearance. But this physical profile only matters in relation to distance. At roughly 8.6 light-years, Sirius is close enough that its light arrives with unusual force. Not close in any human sense, not close in any practical sense. Close only by the merciless standards of interstellar space, where even neighboring stars are divided by distances so large that language starts shrinking them into abstraction. That is the real problem. Human vocabulary makes cosmic scale sound manageable, nearby, neighbor, close. These are dangerous words in astronomy because they smuggle intimacy into places where none exists. Sirius is a neighboring star only in the way a mountain on the horizon is neighboring compared with another continent. The comparison is useful. The intuition is false. And once that false intuition is stripped away, brightness begins to look less like a self-contained trait and more like evidence in a much larger system of relationships. This is the first reframing that matters. Sirius is not bright because brightness belongs to it in some isolated, self-explanatory way. Sirius is bright because a particular star of a particular type exists at a particular distance and is viewed from a particular world under particular optical conditions. The real explanation is relational. The real explanation is systemic. And that matters because systems can hide things that isolated objects cannot. If a star appears simple only because the observer compresses multiple variables into one impression, then the next question becomes unavoidable. What else has been compressed? What else has been mistaken for direct evidence when it is really the visible output of hidden conditions? This is exactly where astronomy becomes more than cataloguing. It becomes a discipline of correction. It teaches the eye to distrust its first certainty. It teaches measurement to intervene where intuition flatters itself. Sirius, for all its brilliance, becomes a lesson in humility. The star that looks easiest to understand is already forcing a deeper method. Separate appearance from cause, separate effect from structure, separate what the sky shows from what the system is. And once that separation begins, Sirius starts shedding its oldest disguise. It is no longer just the brightest point in the night. It becomes a problem in motion, a problem in mass, a problem in hidden companionship. Because when astronomers begin measuring not only how Sirius shines, but how it moves, brightness stops being the central mystery. It becomes the bait. What comes next is stranger. The growing realization that the star everyone can see is being influenced by something they cannot. Long before Sirius became a measured star, it was already a problem for human civilization. Not because people understood what it was, but because they could not ignore what it did to attention, to memory, to time itself. A faint star can disappear into background. Sirius never does. It rises too sharply into notice. It imposes itself on the eye with a kind of authority that predates science and survives it. This is where the modern mind often makes a mistake. It looks back at ancient sky law and sees superstition, poetic projection, symbolic excess. But the story on the surface is smaller than the story underneath. Early cultures were not responding to nothing. They were responding to recurrence, to visibility, to timing, to the practical and psychological force of a celestial object that returned with unusual insistence. They did not know the physics. They knew the pattern. And pattern in pre-modern life is not decoration. Pattern is survival. Sirius enters human history not first as an astronomical curiosity, but as a seasonal signal. It becomes important because it appears at consequential moments, because its reappearance can be linked with heat-flooding harvest cycles, religious observance, and the ordering of communal expectation. The visible star becomes a hinge between sky and society. That does not mean every belief attached to Sirius is accurate in the physical sense. It means the star's prominence gives it cultural leverage powerful enough to shape calendars, omens, rituals, and state symbolism across very different civilizations. Ancient Egypt offers the most famous case, and for good reason. There, the heliacal rising of Sirius, its first visible appearance in the dawn sky, after a period of absence, became deeply associated with the Nile flood and with the renewal of the year. The alignment was not perfect in every century, and the sky itself shifted gradually through precession. But the association was close enough, persistent enough, and important enough that Sirius became entangled with kingship, fertility, inundation, and cosmic order. The star was not just seen. It was integrated. It entered the logic of civilization because it seemed to announce the return of the water on which the civilization depended. That matters. Not because Sirius causes the Nile flood in any direct physical way, but because human societies build meaning from repeated conjunctions long before they disentangle causation from correlation. The real force lies in the system of response. When a star becomes a clock, it also becomes a source of legitimacy. When it marks renewal, it becomes sacred. When it aligns with agricultural and political expectation, it moves from astronomy into structure. The ancient world often linked Sirius to a goddess. The Greeks later identified with Isis, reinforcing how celestial cycles could merge with divine narratives rather than remain abstract observations. This is not evidence of ignorance alone. It is evidence of integration under conditions where the sky is one of the most reliable repeating systems available to human life. In Mesopotamia, in the Greek world, and later in Rome, Sirius also becomes bound to heat and danger to the so-called dog days of summer, as its seasonal appearance is associated with oppressive weather, fever, dryness, and stress. Again, the obvious explanation is not the real one. Sirius does not pour heat into Earth's atmosphere in any meaningful meteorological sense. Its physical influence on terrestrial climate is negligible. Yet that is not what the belief is really about. It is about timing coincidence and symbolic compression. A star that appears in the same seasonal window as extreme heat acquires the reputation of carrying that heat. Once attached, the meaning persists, because it is narratively efficient and culturally useful. The star becomes a messenger of strain. It becomes an emblem of the season's hardest edge. Even the Greek name associated with the dog star carries a sense of scorching intensity. From a distance, this may look like error. More deeply, it is a sign of how human beings recruit the sky into explanatory order when the stakes of timekeeping are high and the environment is not forgiving. That is why Sirius matters far beyond myth as story. It matters as evidence of how observational prominence becomes civilizational weight. A bright, recurring object can do more than inspire legends. It can discipline memory. It can stabilize expectation. It can help convert the sky from spectacle into infrastructure. The deeper truth is not that ancient people were merely enchanted by Sirius. It is that enchantment and utility were never cleanly separate. Sacred things in early societies are often sacred partly because they are useful, and useful partly because they become memorable through sacred framing. Sirius sits exactly in that overlap. Its brilliance gives it mnemonic power. Its recurrence gives it practical force. Its timing gives it consequence. And consequence is what turns a star into a durable social fact. Across cultures, Sirius is repeatedly treated not as one star among many, but as a sign-bearing presence. Sometimes it warns. Sometimes it renews. Sometimes it legitimizes rulers or seasonal rites. Sometimes it marks danger. The specific stories vary, but the pattern remains. Sirius is too conspicuous to remain neutral. That is the key. Human beings do not mythologize every object equally. They mythologize what dominates perception and repeats with significance. The brighter the object, the easier it is to recruit into narrative. The more regular its return, the easier it is to fuse with time. Sirius does both. And that gives it an unusual continuity across eras. It survives the shift from oral tradition to literate culture, from priestly astronomy to mathematical astronomy, from symbolic sky to measured sky. Most objects lose authority when explanation advances. Sirius does not lose it. It changes register. The myths do not vanish because science arrives. They become the outer shell around a deeper account. That transition matters because it reveals a continuity many modern tellings miss. The ancients were not wrong to regard Sirius as important. They were right about importance and incomplete about cause. They sensed significance before they understood structure. That is a recurring pattern in human knowledge. First comes visibility, then meaning, then measurement, then revision. And revision does not erase the earlier layers. It exposes why they formed. Sirius is therefore not merely a star with old stories attached. It is a case study in how the human mind meets the sky first, through awe, then through pattern, then through system. But the next turn is where the comfortable cultural story begins to narrow and break. Because once instruments replace memory as the primary authority, Sirius stops being mainly a seasonal sign and starts becoming something far more disruptive, a source of hard data that refuses to behave like a simple solitary star. A single star should not be able to organize a civilization's sense of season danger and renewal. Sirius does. Or rather, human beings repeatedly make it do so, which is even more revealing. The easy version of the story is that ancient cultures simply noticed a bright star and attached meaning to it. That explanation is too thin. It misses the scale of the relationship. Sirius is not merely named admired or folded into myth as a decorative object. In several major civilizations, it becomes part of the practical architecture of life. It enters agriculture ritual timing, royal symbolism, and seasonal expectation. It helps convert the sky from a background into a schedule. The real problem is not why people told stories about Sirius. It is why one point of light became useful enough, repeatable enough, and psychologically potent enough to serve as a durable anchor for collective behavior. That is a much deeper question because it forces a shift away from myth as ornament and toward myth as operating system. In ancient Egypt, this reaches its most famous form. The heliacal rising of Sirius, its return to visibility just before dawn after a stretch of solar invisibility, becomes associated with the annual Nile inundation and with the beginning of the year. The connection is not perfectly static over long spans of time. Precession slowly alters celestial timing against the calendar. Local conditions affect visibility. The flood itself varies. But none of that weakens the larger truth. For a civilization built on the rhythms of a river, any celestial marker that appears to foreshadow renewal acquires extraordinary force. Sirius becomes entangled with rebirth fecundity, cosmic order, and sovereign legitimacy, because it arrives not in abstraction, but at the edge of material consequence. Water is coming. Fields will change. The political and agricultural order will reset. The sky does not cause the state, but it can help synchronize the imagination that sustains the state. This is where the star stops being just an object and becomes an institution. The achievement is real. The cost is larger. Because once a celestial pattern becomes socially meaningful, it is no longer free to remain merely observational. It becomes encoded into ritual. Priestly knowledge grows around it. Interpretive authority grows around it. What begins as repeated noticing hardens into a framework for expectation, and expectation becomes a form of power. Sirius, in other words, is not only watched, it is administered. The surface story is seasonal timing. The deeper story is social coordination under cosmic signs. And Egypt is not alone. In the Greek and later Roman worlds, Sirius becomes associated with the dog days, the oppressive heat of high summer fever, exhaustion, crop stress, and a general atmosphere of seasonal affliction. That interpretation is physically wrong in the narrowest sense. Sirius does not materially heat the Earth. Its radiation at this distance is negligible in climatic terms. But that objection, while correct, also misses the real mechanism. The belief is not built from laboratory causation. It is built from repeated seasonal coincidence filtered through lived experience. A star rises in the same broad phase of the year as heat intensifies. The environment becomes punishing. Illness seems more common. Fields suffer. Animals strain. The sky acquires blame because the sky provides the most dramatic recurring marker. The star becomes a vessel for concentrated seasonality. It is easier to remember a season if the season has a face. Sirius gives it one. This is not science, but it is not randomness either. It is compression. Human beings reduce diffuse environmental stress into symbolic focus so it can be named, anticipated, and transmitted. That is one reason the dog star persists so strongly in language and imagination. It turns climate into character. It turns a seasonal condition into an arriving presence. Once again, Sirius is not important because ancient people fail to understand the universe. It is important because they are trying to survive in it. The distinction matters. Too many modern accounts flatten pre-modern sky knowledge into a contest between truth and error, as though the only interesting question is whether the ancients got the physics right. They did not. But that is not the full measure of intelligence. The more revealing question is whether they identified recurrent signals capable of organizing labor ritual memory and fear. In that sense, Sirius proves astonishingly effective. It becomes part of the logic by which societies distribute attention across the year. It helps bind astronomical recurrence to human consequence. That is why its cultural career is so long. Brightness gives it authority. Timing gives it utility. Utility gives it ritual weight. Ritual weight gives it endurance. This chain is stronger than any one myth. It survives because it keeps doing work. Even where the specific theological frame changes, Sirius remains difficult to demote. It keeps returning. It keeps arriving at meaningful thresholds. It keeps behaving like more than background. This is the deeper pattern hidden inside ancient sky lore. The heavens are not just interpreted. They are operationalized. A conspicuous star becomes a unit of order. It can mark the year, confirm expectation, intensify fear, or stabilize ceremony. It can join the logic of planting taxation, kingship, or sacred time. Once that happens, astronomy and civilization are no longer separate domains. They become entangled systems. The star is above, but its consequences are below. And the larger the dependence on seasonal rhythm, the stronger that entanglement becomes. Sirius, therefore, occupies a strange threshold in human history. It is both empirical and symbolic at once. People see it with the naked eye. They also load it with meanings that exceed what they see. But this excess is not a failure of reason alone. It is a byproduct of scale. A bright recurring object in a precarious world gathers consequences faster than analysis can regulate them. First comes recurrence, then association, then dependence, then sanctification. The system builds layer by layer until one star is no longer just one star. It is a sign of flood, a sign of heat, a sign of danger, a sign of order, a sign that the year is turning. And yet every one of those meanings still rests on the same underlying fact: a distant physical object emits light, and that light reaches Earth with enough force and regularity to shape civilization before civilization understands the mechanism. That is the real transition point. Because once instrument-based astronomy begins to replace symbolic dependence, Sirius does not become less important. It becomes more dangerous to simple thinking. The myths reveal what the star meant to human beings. The measurements will reveal what the star actually is. And those two things are about to collide. The moment Sirius becomes measurable, it stops being safe for old explanations. A star can carry myth for centuries, because myth does not require precision. Measurement does. Measurement is where admiration begins to lose control of the story, because numbers force distinctions that symbols can hide. The bright star that once serves as omen, calendar warning, and sacred marker now enters a different regime of truth. It is no longer enough to say that Sirius is brilliant, important, or seasonally charged. Those are human descriptions. Astronomy wants physical ones. How far away is it? How fast is it moving? What kind of light does it emit? What mass does it imply? What hidden structures are betrayed by the behavior of that light over time? This is where the familiar star starts becoming dangerous to intuition. Because the more precisely Sirius is observed, the less it resembles the obvious thing it first appears to be. The surface story is visual dominance. The deeper story is that dominance can now be dissected. One of the great revolutions in astronomy is that stars cease to be points and become data. Not visually, at least not at first. Even through telescopes, most stars remain unresolved points of light. But their position, brightness, color, and spectrum can be measured with increasing rigor, and once that happens, the sky changes category. It stops being mainly a theater of appearances and becomes a field of physical evidence. Sirius stands near the center of that transition because it is both conspicuous and close enough to become a target of increasingly exact observation. The first major correction comes with distance. For most of human history, stars are seen without real depth. They appear arranged on a distant shell separated by brightness, but not by measurable three-dimensional placement. That begins to break in the 19th century, when astronomers finally succeed in measuring stellar parallax, the tiny apparent shift in a star's position against more distant background stars as Earth moves around the Sun. The effect is so small that it resists observation for generations, and that resistance itself tells the story. Even the nearest stars are far beyond ordinary imagination. Sirius becomes one of the stars whose distance can be established with real confidence. And once that distance is known, brightness stops being a pure visual impression and becomes a quantitative relationship. A star seen from Earth with a given apparent brilliance can now be assigned an intrinsic luminosity. This is the first decisive separation between what something looks like and what it is. The difference matters everywhere in astronomy, but Sirius makes it vivid because it forces a re-ranking of meaning. A star can look supreme without being supreme in every absolute sense. What matters is not appearance alone, but appearance corrected by geometry. That is the beginning of scientific discipline. The star's place in the sky is no longer enough. Its place in space must be known. Then comes the light itself. To the eye, Sirius is blue-white. That description is useful, but crude. Spectroscopy turns color into structure. Pass starlight through a prism or diffraction device, and what looked like a continuous glow breaks into a spectrum crossed by absorption lines, signatures of chemical elements and physical conditions in the star's outer layers. This is one of the most radical intellectual turns in modern science. Human beings learn not only to see stars, but to read them. They learn that light carries information about temperature composition and motion. A distant star ceases to be unreachable in principle because its radiation becomes a record of its state. Sirius enters that new language and immediately grows more precise. Its spectral character identifies Sirius A as a hot A-type main sequence star, much hotter than the Sun, with strong hydrogen lines and a temperature close to 10,000 Kelvin. This matters because it transforms brightness from a vague impression into a physical output tied to stellar structure. Sirius is not simply bright in the emotional sense. It is radiating energy at a rate consistent with a star of substantial mass and high surface temperature. That sounds like clarification. It is also a trap. Because once astronomers begin combining spectral information, brightness, distance, and positional measurements over time, another pattern emerges, and this one cannot be explained by luminosity at all. The star moves, not just across the sky in the broad sense that many nearby stars do, but with subtle irregularities that suggest dynamical influence. This is where the easy explanation fails again. If Sirius was simply one luminous star moving through space, its motion should be predictable within the limits of measurement. But careful observations begin indicating that something more is involved. The visible star behaves as though it is responding to another mass, not a nearby background object by coincidence, not an optical artifact, a real gravitational partner. The problem is that this partner is not initially seen, and that matters more than it first seems. Astronomy had already learned to measure visible things. Sirius now pushes it toward inferring invisible ones. That is a deeper threshold. It means a star can reveal another object, not by shining on it, but by failing to move like a lone body should. This is one of the great conceptual escalations in science, the transition from observing objects directly to detecting them through consequences. The eye no longer reigns alone. Inference becomes central. The system beneath the light starts to appear. And Sirius, the star once treated as the most obvious object in the sky, becomes one of the clearest demonstrations that obviousness can be physically misleading. The achievement is real. Precision has stripped myth away from the star's brightness and replaced it with distant spectrum mass and luminosity. But the cost is larger. The more exact the measurements become, the less stable the simple picture remains. Sirius is not settling into clarity. It is opening into complication. Its light says one thing, its motion says another. The visible star seems sufficient until the orbital evidence begins to accumulate. Then sufficiency collapses. The system no longer explains itself as one bright sun hanging in local space. It begins to point stubbornly and repeatedly to an unseen companion whose presence can be denied only by ignoring the data. That is the next great descent. Sirius is no longer just a star to be measured. It is becoming a case in which measurement forces belief in something hidden. The obvious explanation fails the moment Sirius refuses to behave like a star that is alone. Up to this point, the system can still be mistaken for a triumph of clarification. Ancient symbolism has given way to distant spectrum temperature and luminosity. The bright point in the sky has become a physical object with measurable properties. That feels like progress towards simplicity. It is progress, but not toward simplicity. It is progress toward exposure. Because the deeper astronomy looks, the more Sirius begins to act like a star under influence. Not metaphorically, dynamically. Its motion contains a disturbance, a pattern of deviation that cannot be explained away as observational noise once the measurements improve enough and the persistence becomes undeniable. This is where the story stops being about what Sirius is and starts becoming about what Sirius is hiding. The visible star does not merely travel, it wobbles. It shifts as though responding to another mass. The real problem is not brightness, it is orbit, and orbit is merciless. A star may mislead the eye, but gravity does not flatter appearances. If Sirius A were truly alone, its path through space should reflect only its own motion and the larger gravitational environment of the galaxy. Instead, its observed behavior points to a local partner, something close enough and massive enough to force the luminous star into a mutual dance around a shared center of mass. That concept matters. The brighter object is not the immovable center just because it dominates the view. In a binary system, both bodies orbit, both yield, both are governed by the same underlying rule. The one that looks sovereign from Earth may still be displaced, tugged and made to reveal another presence through its own departures from expected motion. This is one of the most important reversals in the entire story. Sirius. The star that appears most self-sufficient becomes evidence of dependence. The achievement of 19th century astronomy is not just sharper seeing. It is the growing willingness to trust inference when direct sight falls short. This is not blind speculation. It is structured reading of consequence. Friedrich Bessel, one of the great astronomers of the 19th century, notices in the 1840s that the motions of Sirius and Procyon cannot be neatly reconciled with the assumption that each is a solitary visible star. He proposes that each is being perturbed by an unseen companion. That claim is radical in exactly the right way. It does not invent a mystery for drama. It submits to one because the data demand it. The visible star's motion is incomplete as an explanation of itself. Something else must be there. The logic is severe. If a body moves as though gravitationally influenced, then either the law has failed or an unseen mass is present. The law does not fail here. The unseen mass becomes the necessary answer. This is a crucial intellectual threshold. Astronomy moves from cataloging what can be seen to proving what cannot. Sirius becomes one of the clearest early demonstrations that invisibility is not absence. The story on the surface is still a bright star. The story underneath is now a dynamical system exposing one hidden object through the behavior of another. That is a much deeper kind of seeing, and it changes the discipline. Once invisible companions become credible, the sky is no longer limited to what enters the eye or the telescope directly. It becomes a place where consequences carry as much authority as images. But Sirius does not yield its second body immediately. The companion is predicted before it is plainly observed, and that delay matters because it tests whether astronomy is really prepared to follow evidence into uncomfortable territory. Prediction without sight always carries risk. It invites doubt. It invites the suspicion that instruments' assumptions or calculations are imposing a phantom on the sky. Yet the pattern holds. The deviations in Sirius A's motion remain too consistent to dismiss. And then, in 1862, while testing a large refracting telescope, Alvan Graham Clark observes the faint companion near Sirius. The hidden partner appears. The inference is vindicated. The invisible cause becomes visible after all. But even this moment of confirmation does not resolve the system into comfort. It does the opposite. Because the companion is not what an easy imagination would expect. If there is another object massive enough to disturb Sirius A, then perhaps it should look like another ordinary star, merely fainter or smaller. Instead, the companion appears strangely dim for something with such gravitational significance. This is where the accepted explanation breaks again. Discovery does not close the mystery, it sharpens it. The second body exists. That much is settled. But what kind of object can carry substantial mass while emitting so little light compared with the blazing primary? This only looks like a solved problem from a distance. Up close, it becomes more destabilizing than before. The new object, later called Sirius B, is not just a companion. It is a contradiction delivered by observation itself. Here the narrative changes scale. Until now, the hidden layer beneath Sirius is structural. The bright star is really a binary. That is already enough to shatter naive perception. But the next layer is physical and far stranger. The companion's faintness is out of proportion to the role gravity assigns it. The visible hierarchy of the system no longer matches the dynamical one in any simple way. This is the moment when binary motion stops being a mere technical detail and becomes a doorway into extreme stellar evolution. Sirius A is no longer the whole star story. It is half of one, and the half no one expects is the more disruptive one. Because what begins as an unseen companion, inferred from orbital irregularity, is about to become one of the first great lessons in degenerate matter-stellar death, and the possibility that a star can collapse into something tiny, dim, and almost beyond ordinary comprehension without ceasing to possess enormous mass. The brightest star in the sky has now exposed a partner that should not make intuitive sense. And the real shock is still ahead. When Sirius B finally enters view, it does not behave like a revelation that makes the system easier to understand. It behaves like a revelation that makes ordinary understanding collapse. The hidden companion is there. The orbital inference is correct. The bright star in the sky is not alone. That much should have brought relief. Instead, it creates a deeper instability, because the newly seen object does not fit the scale of the force it seems to exert. This is the point where the story changes from detection to contradiction. Astronomers now know that Sirius A has a partner, but the partner appears faint small and visually unimpressive beside the blinding primary. That should imply low significance. It should suggest a modest secondary star, some lesser companion riding beside the dominant beacon. But gravity does not agree. The motion of the system says the companion matters far more than its light suggests. And that mismatch between luminosity and mass is where the real descent begins. The easy assumption is that stars advertise themselves honestly. Bright stars are important. Dim stars are minor. Strong gravitational players should look powerful. Sirius B destroys that hierarchy. It appears like a ghost beside a floodlight, yet the system's orbital behavior says this ghost carries serious weight. The visible ranking is false. The real ranking lies beneath the light. This only looks simple from a distance. Once astronomers start estimating the properties of the companion more carefully, the contradiction sharpens into something extraordinary. Sirius B is faint, yes, but not because it is trivial. It is faint because it is tiny by stellar standards, not diffuse, not underdeveloped, compressed. That distinction changes everything. Here the imagination begins to fail in the precise way astronomy so often forces it to fail. Most people, when they think of a star, think of something vast, flaming, swollen with energy, enormous, almost by definition. Even small stars are expected to be large compared with planets. Sirius B violates that expectation so completely that the first correct descriptions sound almost like category mistakes. The object contains roughly the mass of the Sun, yet its size is comparable to Earth. That sentence is easy to say and nearly impossible to feel. A stellar mass inside a planetary volume. A sun-sized quantity of matter packed into a world-sized sphere. This is not merely unusual. It is a direct assault on everyday intuition about matter itself. The real problem is not that Sirius B is dim. The real problem is that it is dense beyond ordinary experience. Density in daily life is a manageable idea. Stone is denser than wood. Iron is denser than stone. Water is denser than air. Human intuition can climb those steps. It breaks here. In a white dwarf like Sirius, B matter is compressed to the point that a teaspoon of it, if somehow brought to Earth intact, would weigh tons. The comparison is famous because the raw numbers are otherwise too abstract to grip. Even then, the mind resists. Matter is supposed to occupy space according to the loose rules of familiar objects. Here, those rules are gone. Atoms are no longer arranged with ordinary emptiness between them. The star has been forced into a state where gravity has driven matter into a radically compact form, and the resistance that prevents further collapse is no longer ordinary thermal pressure in the way it is inside a living main sequence star like Sirius A. This is the threshold where the system stops being about stars in the conventional sense and starts becoming about the fate of stars after ordinary fusion-driven life has ended. Sirius B is not a second bright sun. It is the remnant of one. That word matters, remnant. It means the visible object is not an early stage, but a late one. Not a lesser beginning, but the compressed aftermath of a much larger stellar history. Once long before human beings ever watched Sirius from Earth, the star that became Sirius B was likely more massive than Sirius A. That is the only reason it could evolve faster and reach death first. The system therefore contains a hidden reversal. The dim companion was once the dominant star. The blazing primary, which now rules the sky and commands attention, is in a sense the younger survivor of a slower life track. The story on the surface is brightness. The story underneath is sequence, mortality, and inversion. The fainter object may be the more historically powerful one. That reversal gives Sirius B unusual narrative force, but the physics is even more severe than the symbolism. A white dwarf is not shining because it is sustaining full-scale hydrogen fusion in its core the way a main sequence star does. It shines because it is hot and because it is radiating stored thermal energy, the lingering heat of a former stellar life after the outer layers have been shed and the core has been left exposed. Sirius B is therefore both dead and not dead in the everyday sense. Nuclear life as a normal star is over. Thermal radiance remains. The star has ceased to be what it was, yet it has not vanished. It endures as a compact ember of a stellar past, dense, hot, and gravitationally formidable. That is why calling it a ghost is not just poetic. It is structurally accurate. Sirius B is the visible remainder of a star that once expanded, changed, exhausted its core fuel, and discarded much of itself to leave behind something small enough to seem minor and powerful enough to defy that impression completely. The achievement is real. Astronomy has moved from mythic brightness to measured distance from apparent singularity to binary motion, from hidden companion to direct observation. But the cost is larger. Each step has revealed that Sirius is less like the obvious star it first appears to be, and more like a layered archive of stellar evolution. The companion is not just there. It is a warning embedded beside the brightest star in the sky. It says that luminosity is temporary. That size is not permanence, that a star can lose almost everything people associate with starhood, and still remain massive, hot, and dynamically decisive. Sirius A still blazes with present tense power. Sirius B stands beside it as future aftermath and contradiction. And once that contradiction is fully faced, the next question becomes unavoidable. What kind of physics can possibly hold up an object like this against the crushing force of its own gravity? The real shock of Sirius B is not that a star has died. Stars die everywhere in the galaxy. The real shock is the form that death takes when gravity is allowed to finish its argument. Most endings in nature suggest reduction, dispersal, collapse into insignificance. Sirius B does collapse, but not into insignificance. It collapses into pressure so extreme that matter itself is forced into an unfamiliar regime. This is where the story stops being merely astronomical and becomes almost confrontational. Human intuition can accept that stars burn. It can accept that stars cool. It can even accept that stars explode. What it does not accept easily is that a star with roughly the mass of the Sun can be compressed into a sphere about the size of Earth and remain there in stable existence. That sounds less like an ending than a violation, but the violation is only against common sense. The physics is relentless. Once a star like the progenitor of Sirius B exhausts the fuel needed to support its core, in the ordinary way, the balance that defines stellar life begins to fail. For most of a star's active lifetime, gravity is pushing inward, while pressure generated by hot plasma and nuclear fusion pushes outward. That equilibrium is the real engine of a living star. It is not rest. It is a truce. The visible radiance is the surface consequence of a much deeper war between inward collapse and outward support. A main sequence star survives because the outward side of that war keeps renewing itself through fusion in the core. But that arrangement is temporary. The fuel changes. The core composition changes. And eventually the old support system is no longer enough. This is the moment when a star reveals what it is made of, not chemically, but structurally. The obvious explanation is not the real one. A star does not stay up because it is hot in some vague sense. It stays up because pressure generated under specific internal conditions keeps gravity from winning outright. When those conditions fail, gravity does what gravity has always been trying to do. It compresses. It drives matter inward. It strips away ordinary scale. For a star in the mass range relevant to Sirius B's history, this collapse does not continue forever. It does not produce a neutron star. It does not produce a black hole. It reaches a different threshold. The core is packed so tightly that quantum mechanics, not ordinary thermal pressure, becomes the last line holding the structure up. This is where the story becomes stranger than the familiar language used to tell it. A white dwarf is supported by electron degeneracy pressure, a consequence of the Pauli exclusion principle, which prevents electrons from occupying the same quantum state in the same way. That sentence is often recited as if it explains itself. It does not. What it really means is that nature has rules deeper than heat, and when gravity pushes matter hard enough, those deeper rules become load-bearing. Matter resists being compressed into identical quantum arrangements. That resistance is not a matter of preference. It is built into the structure of reality. Sirius B exists because the universe refuses to let electrons be stacked without limit. The star is therefore not held up by fire in the ordinary sense. It is held up by a quantum prohibition made macroscopic. That is one of the great hidden revelations of modern physics. The sky does not merely contain distant objects. It contains places where the logic of the microscopic world becomes the architecture of the visible universe. Sirius B is one of those places. This only looks like a small dim star from a distance. In truth, It is a stellar core whose continued existence depends on laws that most human beings encounter, if at all, only in textbooks. The cost of compression is scale beyond intuition. Sirius B packs about a solar mass into a radius only a little larger than Earth's. Its surface gravity is immense. Its density is staggering. Its escape velocity is so high that even light climbing away from its gravitational field is measurably affected, producing a gravitational redshift that helped confirm how extreme the object really is. That matters because it ties theory back to evidence. The white dwarf is not merely a beautiful idea built from equations. It is a physical object whose properties leave observable marks. Its spectrum, its orbit, its temperature, its mass-radius relationship all converge toward the same conclusion. Sirius B is not pretending to be impossible. It is teaching astronomers that possibility was always wider than intuition allowed. And the deeper truth is even harsher. This kind of support has limits. Electron degeneracy pressure can resist gravity only up to a point, beyond roughly 1/4 solar masses. The Chandrasekhar limit, a white dwarf can no longer remain stable in this form. That number matters because it reveals that even in this bizarre quantum-supported state, nature is not offering unlimited rescue. It is offering a threshold. Stay below it, and the remnant can endure as a white dwarf. Exceed it and collapse must continue into something even more extreme. Sirius B survives because it falls on the stable side of that divide. But the existence of the divide changes the meaning of the star. It is not simply a dead object. It is an object balanced at a permitted edge of reality, allowed to persist because its mass and structure fit within the rules. The story on the surface is that Sirius has a white dwarf companion. The story underneath is that one of the brightest systems in the sky contains a visible demonstration that quantum mechanics is not confined to laboratories or subatomic diagrams. It governs the remains of stars. It determines which stellar corpses survive in one form and which are driven into another. Sirius B is therefore not just an astronomical curiosity. It is a compressed proof that the universe runs deeper than appearances suggest. The bright star Sirius A still looks like the main story because light dominates attention. But the companion is where the system's deepest physics is exposed. It shows what happens when a star loses the battle to remain ordinary, yet does not fall all the way into catastrophe. It is matter under siege, matter stripped of familiar spaciousness, matter forced into obedience by gravity until quantum law says no further. And once that is understood, Sirius B stops looking like a side note to a brighter star. It becomes a warning, a precedent, and a preview. Because the white dwarf is not just a strange object beside Sirius A, it is a glimpse of how stellar life ends, and of the fate that even the brighter star cannot escape forever. The phrase, dead star, sounds final. Sirius B proves it is not. Death, in ordinary language, suggests silence, passivity, the end of influence. But a white dwarf is not silent in any meaningful dynamical sense, and it is certainly not passive. The nuclear life of the star is over. The old core fusion that once made it a main engine of stellar radiance is gone. Yet the remnant still governs, still pulls, still radiates heat, still shapes the architecture of the system around it. That is the contradiction at the center of Sirius. The brighter star looks alive and dominant. The dimmer star is the one that has already crossed the threshold of stellar death. But the story on the surface is smaller than the story underneath. Sirius B is not an inert ruin parked beside a blazing neighbor. It is an active survivor of a prior era, and the system cannot be understood without recognizing how much of its present is organized by that past. This matters because people instinctively imagine stellar evolution as a sequence of isolated snapshots. First, a star forms. Then it shines. Then it changes. Then it dies. One stage replaces another. The older state disappears and the newer one takes over. Real systems are less clean than that. A remnant carries history forward. It preserves the consequences of earlier mass, earlier structure, earlier rates of evolution. It continues to exert force long after the visually dramatic phase has ended. In Sirius, that force is not theoretical. Sirius A and Sirius B orbit a common center of mass with a period of about 50 years, in a notably elongated orbit, meaning the bright primary does not simply coexist with the white dwarf. It is continuously responding to it. Even now, the dead star still writes motion into the living one. That is the first reframe that matters. Death here is not disappearance. It is transformation into a different kind of power. Sirius B does not dominate by light. It dominates by gravity, by density, by historical precedence, by being the first member of the system to complete the life cycle that Sirius A is still moving through. In a sense, the dim companion has already seen the future of the system. It has already crossed the border that the brighter star has not. That makes it more than a remnant. It makes it a kind of forecast embodied in matter. The real problem is not that Sirius B is dead. It is that dead does not mean irrelevant. In fact, in this system, dead may be the more revealing state. A living main sequence star like Sirius A is impressive but familiar in the broad logic of astrophysics. Hydrogen fuses in the core. Pressure balances gravity. Luminosity pours outward. The star shines because the machine is still running. Sirius B reveals the machine after failure, after contraction, after the outer layers are gone, and only the compact record of previous existence remains. That is where the deeper physics sits. That is where consequences become visible. And because the remnant is still there, still bound into the system, the history of one star becomes part of the ongoing environment of the other. This is where binary stars stop being a matter of paired objects and become a matter of shared consequence. Sirius A is not orbiting beside a neutral artifact. It is orbiting beside the compressed result of everything Sirius B once was. The system therefore contains two temporal layers at once. One star is still in a stable luminous phase. The other is the dense aftermath of a completed stellar life. Present and future appear together. Vitality and aftermath share one orbit. It is difficult to overstate how unusual that makes Sirius as an object of human attention. To the naked eye, it is a brilliant point. In physical terms, it is a nearby demonstration that stellar grandeur and stellar ruin can coexist in a single visible system. The achievement is real. Astronomy has learned to detect resolve and characterize a white dwarf beside the brightest star in the sky. But the cost is larger. Because once Sirius B is understood as an enduring gravitational presence rather than a dim footnote, the entire emotional geometry of the system changes. Sirius A no longer reads as uncomplicated brilliance. Its light now sits beside a compressed warning, not a symbolic warning invented by myth, but a material one written by evolution. This is what a star can become. This is what remains after luminosity loses its old form. This is what waits beyond the apparent stability of stellar life. And because Sirius B likely began as the more massive star, its current condition also reveals another hard truth about the universe. Greater mass can mean shorter life. More impressive beginnings can mean faster collapse into aftermath. The brighter story is not always the longer one. The star that once may have dominated the system is now the smaller-looking object stripped down to core remnant and residual heat. The hierarchy has reversed. That reversal matters because it destroys one more intuitive habit the belief that what looks strongest now must always have been strongest or will remain so. Sirius teaches the opposite. Stellar power changes form. Dominance migrates from one kind of presence to another. First, the more massive star evolves faster and dies. Then its remnant continues to govern by gravity, even while a less evolved companion takes over visually. The system is not static. It is layered, time-made orbital, and that layered time leads directly to the next unavoidable question. If Sirius B is the future in compressed form, what does that future imply for Sirius A itself? The brightest star in the night sky still burns with present tense confidence. But beside it orbits proof that confidence is temporary, and that even stars which seem overwhelming from Earth are only passing through a phase on their way towards something smaller, denser, and far less forgiving. The future of Sirius is already visible, and that is what makes it unsettling. Most stars conceal their endings behind timescales too large for the human mind to feel. Sirius does not conceal them quite so completely because the system places a still living star beside the compressed remnant of one that has already finished the journey. The result is not just a binary. It is a before and after image written into one orbit. Sirius A blazes now with all the authority of stellar youth in relative terms, blue-white, massive, hot, and visually dominant. Sirius B circles beside it as the stripped core of a former star, small, dim, and brutally dense. The obvious interpretation is that these are simply two different objects in two different states. The real interpretation is harsher. One is also a preview of the other, not in every detail, not with perfect symmetry, but in the broad logic of stellar evolution. Sirius B is the system's warning that radiance is temporary, and that even stars which seem stable for millions of years are only occupying a phase, not a permanent identity. That is the deeper truth hidden inside all bright stars. They do not possess brilliance. They pass through it. Sirius A is an A-type main sequence star roughly twice the Sun's mass, and far more luminous, which means it burns hotter and faster than the Sun. That is an advantage only if the goal is spectacle. It is not an advantage if the goal is duration. Greater mass drives higher core temperatures and faster nuclear consumption. The achievement is real. Sirius A shines with extraordinary force. The cost is larger. It is spending its fuel more aggressively, and stars that burn harder do not earn longer lives. This is one of the most important reversals in all of stellar astrophysics. Human intuition associates greatness with endurance. The universe often does the opposite. The more massive the star, the more rapidly it moves through its central hydrogen-burning lifetime. Sirius A will not live as long as the Sun. Its brilliance is inseparable from its brevity. That does not mean imminent collapse in any human time frame. The star remains stable on scales far beyond civilization, but astrophysical stability is not permanence. It is scheduled transition. At some point, after exhausting the hydrogen in its core, Sirius A will begin leaving the main sequence. The balance between gravity and fusion that now defines its ordinary life will change. Core structure will shift. Outer layers will respond. The star will expand into a giant phase, becoming cooler at the surface, even as internal changes drive new forms of fusion and structural rearrangement. This is where the bright, familiar star begins to detach from the visual identity by which Earth knows it. The Sirius that dominates the night sky now is not the Sirius that will exist forever. The name remains. The star changes category. That change matters because it reveals that the night sky is not a gallery of fixed personalities. It is a field of temporary states. A main sequence star is not a kind of eternal object. It is a chapter. Sirius B proves what lies beyond that chapter. Once the giant stages are complete and the star sheds its outer layers, what remains will be the hot, compact core, another white dwarf. Not a replica of Sirius B in every parameter, because initial mass evolutionary timing and exact remnant mass differ, but the family resemblance will be fundamental. The brightest star in the sky will eventually become a dense stellar ember. The flood of visible authority will contract into a remnant with planetary scale and enormous density. That is the real problem with calling stars eternal. They are not. They are machines that spend themselves. The most stable-looking stars are often the easiest to misread, because their timescales are longer than memory and politics and even civilizations. Sirius A, therefore, occupies a deceptive middle ground. To human experience, it is effectively permanent. To physics, it is already on a track with an ending type we know in advance. This only looks uncertain from a distance. The broad arc is clear. Main sequence burning. Expansion. Mass loss. White dwarf remnant. The unresolved details are smaller than the trajectory itself, and that clarity gives Sirius unusual interpretive power. Most people can look at a star and imagine it as an isolated present. Sirius asks for something more disciplined. It asks the observer to hold the present and the future in the same frame. It asks the observer to see that the companion is not merely next to the bright star, it is ahead of it in evolutionary time. That is why the system feels almost narrative in structure. Sirius A is the visible present. Sirius B is the compressed future made tangible. One still burns with ordinary stellar life. The other has already survived the collapse of that life into a remnant state governed by different internal rules. This reframes the whole system. Sirius is no longer just about brightness, or even just about binarity. It becomes a lesson in sequence inasymmetry, in the brutal efficiency with which mass sets destiny. The brighter star is not more secure because it is brighter. It is merely earlier in one part of the process, and that process carries consequences beyond the individual stars themselves. When Sirius A eventually changes the entire system's geometry of light, mass loss and orbital meaning will shift again. The pair Earth knows as the brightest star system in the night sky will become something visually and physically different, less spectacular to the eye, perhaps, but no less real in its underlying structure. The story on the surface is about what Sirius is now. The story underneath is about what the system guarantees it will become. That guarantee is the source of the system's strange power over the imagination. It takes a point of light and turns it into a life cycle. It takes beauty and inserts mortality directly into it. And once Sirius A is understood not as a permanent beacon, but as a star moving toward the same broad endpoint already embodied by Sirius B, the next simplification also begins to fail. Because Sirius is not merely one bright star plus one dead companion. It is a binary system whose members have shaped, constrained, and redefined each other the entire time. The phrase single star is one of astronomy's most useful conveniences and one of its most dangerous illusions. Sirius exposes that danger with unusual clarity. To the eye, it is one brilliant object. To physics, it is a binary system, and that difference is not a technical footnote. It is the real story. The mistake people make is to imagine that a companion simply adds another object to the scene, as if the system were just a primary star plus a secondary one placed nearby. But binary stars are not objects arranged beside each other in static coexistence. They are mutual problems. They are negotiated systems of gravity timing separation and consequence. Each member changes the meaning of the other. Each orbit is a record of shared constraint. Sirius is not one bright star with an appendix attached. It is a relationship written in motion. That is the first reframe that matters. The visible brilliance of Sirius A encourages a false hierarchy. It suggests a sovereign primary and a minor secondary, a main actor and a dim supporting body. That visual ranking is emotionally natural and physically incomplete. In a binary, the center is not where the brighter star appears to be. The center is the system's common center of mass, the barycenter around which both bodies orbit. Even when one star dominates the light, it does not dominate the laws. This matters because it destroys the intuition that brightness grants centrality. Sirius A is the more radiant member, but it still moves in response to Sirius B. It yields, it curves. It is displaced by a companion far dimmer to the eye, but substantial in mass. The real problem is not which star looks stronger. It is how their shared gravitational structure redistributes power. This only looks simple from a distance. Up close, binary systems teach one of the hardest lessons in astronomy. No star is fully understood in isolation if its history and present are tied to another body. Sirius A and Sirius B orbit each other with a period of about half a century, and their separation changes significantly over the course of that elongated orbit. Sometimes they are relatively farther apart, sometimes closer, and that changing geometry has shaped not only how difficult the companion is to observe against the glare of the primary, but also how astronomers have come to understand the system's mass orientation and long-term behavior. Every orbit is data. Every position angle, every separation measurement, every shift against expectation helps tighten the physical model. In that sense, Sirius is not merely a spectacular system, it is a calibrating one. Binary stars are among the most important tools in astrophysics because orbital motion lets astronomers infer masses with a rigor unavailable for isolated stars. Mass is the hidden master variable of stellar evolution. It governs temperature, luminosity, lifespan, and fate. Yet mass is rarely measured directly. It must be extracted from motion. Sirius, through its binary nature, offers exactly that. The brightest star in the sky becomes one of the clearest demonstrations that motion reveals what light alone cannot. The obvious explanation is not the real one. The brightness tells part of the story. The orbit tells the rest. Once masses are estimated from the system's dynamics, the deeper logic of the pair becomes harder to ignore. Sirius B, though tiny in size and faint in visible light, emerges as an object with about a solar mass. Sirius A comes in at around twice that. These are not trivial numbers. They mean the companion is not some decorative residue floating beside the primary. It is a major gravitational participant. And because it is a white dwarf, its current state encodes a prior life in which it likely began even more massive than Sirius A, before shedding much of its original mass during later evolutionary stages. This is where binary thinking becomes more powerful than single-star thinking. The system is not just two stars frozen at one moment. It is two histories intersecting. The star that now looks dominant was once the slower evolving partner. The one that looks subordinate was once likely the more massive and faster evolving star. Present visibility and historical precedents have diverged. The hierarchy has been rearranged by time. That is why binary systems resist simple storytelling. They contain hidden reversals, delayed consequences and asymmetries that only make sense when both objects are treated as parts of one larger machine. Sirius is not merely about companionship. It is about how companionship changes interpretation. A solitary Sirius A would still be an impressive nearby star, but it would not carry the same weight as a lesson in stellar evolution, mass determination, and remnant physics. A solitary Sirius B, if somehow isolated and discovered alone, would still be a fascinating white dwarf. but it would not have the same dramatic force as the compact ghost orbiting the brightest star in Earth's night sky. Together, they produce a deeper effect. They force the observer to compare states, lifetimes, densities, and futures inside a single bound system. They turn abstraction into juxtaposition. They make the invisible architecture of stellar evolution easier to grasp because it is distributed across two connected objects rather than one long theoretical timeline. The achievement is real. Binary structure makes Sirius legible in ways a single star could never be. But the cost is larger, because once the system is understood relationally, even more complicated possibilities come into view. In many binary systems across the galaxy, stars exchange mass, distort one another's envelopes, trigger novae spiral inward, or evolve into explosive endpoints. Sirius is not currently such a catastrophic interacting binary. Its separation is large enough that no dramatic mass transfer is now occurring between Sirius A and the white dwarf. But that absence is itself instructive. It reveals that not all binaries become violent in the same way. Some shape each other more subtly through orbital history, evolutionary timing, and the shared context each provides for interpreting the other. The story on the surface is one bright star with a dim companion. The story underneath is a system that teaches how stars live, not alone, but in structures under constraints in relationships governed by mass and distance, rather than by human categories of importance. And once Sirius is seen this way, another illusion begins to fail. Its dominance in Earth's sky no longer seems like an absolute fact about cosmic superiority. It begins to look like something more contingent, a result not only of what Sirius is, but of where Earth happens to be when it looks. The brightest star in the night sky is not the most powerful star in the galaxy, and that distinction is the one most people never make. Sirius feels absolute because it dominates the human view so completely. It rises, and lesser stars recede into comparison. It flashes through the atmosphere with such intensity that the eye treats it almost like a verdict. This is the king of the night. This is the summit of stellar brightness. But that is only true from one place under one set of conditions for one species of observer standing on one small world inside one narrow region of the Milky Way. The real explanation is not supremacy. It is perspective. Sirius dominates our sky because luminosity and distance happen to converge in our favor. That sounds straightforward until the scale becomes visible. Sirius A is intrinsically bright, far brighter than the Sun, with a blue-white radiance produced by a hotter surface and greater energy output. But the universe contains stars vastly more luminous than Sirius. Enormous blue supergiants, unstable giants, and extreme stellar engines outshine it by huge factors in raw power. Most of them simply do not matter to the naked eye in the same way because they are too far away. This is where astronomy repeatedly humiliates intuition. Human beings do not see the cosmos ranked by magnitude of being. They see it filtered by distance. The sky is not a hierarchy of true importance. It is a projection shaped by position. What appears dominant may be merely nearby. What appears modest may be unimaginably greater and unimaginably farther away. Sirius is the perfect lesson in that distortion because it is bright enough to feel like cosmic first place, while being in a larger galactic sense, a local standout, rather than an ultimate extreme. This only looks simple from a distance. The deeper truth is that apparent brightness is one of the most observer-dependent properties in all of astronomy. A star's absolute luminosity is a physical fact about the star. Its apparent brightness is a fact about the relationship between that star and the observer. Move the observer and the sky is rewritten. Move Earth a few dozen or a few hundred light years, and Sirius loses its throne. Move some other star closer, and the familiar hierarchy collapses. The night sky most people take as permanent is really a temporary arrangement produced by location. That is one reason the heavens feel stable while being profoundly contingent. Human time is too short to watch the full map change, so the present arrangement masquerades as eternal. It is not. The constellations drift. Nearby stars move. The brightest objects in the sky today are not the brightest objects that ancient humans saw in the exact same positions, and they will not remain so forever. Sirius itself has proper motion through space. Over long enough intervals, even its relation to Earth changes. The star that seems fixed is only fixed on a timescale mercifully small enough for human confidence. This reframes the entire emotional meaning of its dominance. Sirius is not bright because the universe singled it out for Earth. It is bright because Earth happens for now to occupy a place from which Sirius's light arrives with unusual authority. The story on the surface is one of stellar majesty. The story underneath is geometry. That does not make the brightness less impressive. It makes it more interesting. Because once perspective enters the explanation, the star becomes a case study in how reality and experience diverge. Human beings live inside apparent rankings. Closest, brightest, largest looking, most obvious. Science keeps showing that these categories are not false so much as incomplete. They are local truths. Sirius is indeed the brightest star in the night sky, as seen from Earth. But Earth is not the center of the relevant frame. It is only the seat of the experience. That distinction matters everywhere in astronomy, and nowhere more elegantly than here. The obvious explanation is that Sirius dominates because it is simply better at being a star. The real explanation is that it is luminous enough and close enough to outcompete rivals from our vantage point. That is a subtler and more unsettling truth, because it denies the comfort of absolute rankings. It says, the universe does not arrange itself around human perspective, even when human perspective feels decisive. There is another layer here as well. The atmosphere itself helps dramatize Sirius for observers on Earth. Because the star often appears relatively low in the sky, for many populations, its light passes through thicker, more turbulent columns of air. That amplifies twinkling and color flashing, making Sirius seem even more alive, unstable, and commanding than stars seen higher overhead. The visible intensity is therefore not just astrophysical. It is performative through environment. Earth helps stage the star. Again, the pattern repeats. What looks like a simple property of the object turns out to be the result of a relationship between object distance observer and medium. Sirius does not merely shine. It arrives through conditions. This is why it has carried such cultural force for so long. It is not just intrinsically notable, it is experientially overwhelming. And experience is what builds memory symbolism and false simplicity. The achievement is real. Astronomy has explained why Sirius dominates the sky without appealing to myth or exaggeration. But the cost is larger. Because once brightness is understood as contingent, the star loses its last claim to being interpreted at face value. It is no longer enough to say Sirius is the brightest and leave the sentence closed. Brightest to whom? Brightest from where? Brightest under what conditions? These are not semantic tricks. They are the beginning of intellectual honesty. And that honesty opens a harder recognition. Familiarity has hidden how unusual the system really is. The star is famous, named, mythologized, and repeatedly seen, which makes it feel normal. But the more precisely it is understood, the less normal it becomes. A luminous nearby star paired with a dense white dwarf remnant is not an ordinary image of the heavens. It is a rare convergence that only feels commonplace because people have been looking at it for so long. Familiar things are often the hardest to see clearly. Sirius proves it. Not because it is faint, distant, or elusive, but because it is too well known. It has a name people remember. It has a place in myth navigation, popular astronomy school lessons, and seasonal memory. It is pointed out early, identified easily, and revisited often. That should make it better understood. In practice, it often does the opposite. Repetition strips away shock. Recognition creates the illusion of completion. The star becomes so culturally settled that its strangeness is absorbed into normality. This is the hidden cost of familiarity. What is seen most often is not always examined most deeply. The easy version of Sirius is a bright nearby star with a dim companion, accurate enough to begin. Inadequate, the moment-scale history and physics are taken seriously, because there is nothing ordinary about the actual combination involved. A hot, blue-white main sequence star around twice the mass of the Sun. A white dwarf companion with roughly solar mass compressed into Earth-like size. A binary orbit close enough in cosmic terms to be one of the most important local stellar systems, yet visually presented to naked eye observers as one unmistakable point. A system embedded in ancient cultural memory and modern astrophysical significance at the same time. None of that is normal in the everyday sense. None of it deserves to feel familiar. The story on the surface is that Sirius is famous because it is bright. The story underneath is that brightness made it so famous that people stopped feeling how unusual the system truly is. This only looks simple from a distance. Up close, Sirius is almost perversely layered. It is one of the few stars known across deep time to both pre-modern skywatchers and modern astrophysicists in very different ways, and it remains central in both registers for different reasons. Ancient observers care because it is visually dominant and seasonally consequential. Modern science cares because it is close, bright, binary, and physically revealing. The overlap is rare. Most stars that dominate science do not dominate cultural memory. Most stars that dominate cultural memory do not end up carrying such a rich payload of stellar evolution, quantum matter, and orbital inference. Sirius does both. That should make it unforgettable in the strongest sense. Yet the opposite often happens. Because the star is so famous, it gets flattened into the category of the bright one. Fame simplifies what should remain complex. This is not unique to astronomy. Human attention routinely reduces well-known things into labels. Once something is named and filed away, the mind stops demanding explanation. Sirius becomes not a question, but an answer. It is the brightest star. It is the dog star. It is over there near Orion. Identification replaces inquiry. The real problem is not ignorance. It is premature closure. The mind thinks it already possesses the object because it possesses the label. And labels are cheap. Sirius is expensive. It contains too much history and too much physics to fit inside the easy confidence that familiarity produces. Consider what has already been uncovered beneath that label. A system once read as omen and seasonal marker becomes measurable in distance and luminosity. A single apparent star turns into a binary. A faint companion becomes a white dwarf. A white dwarf becomes evidence that quantum mechanics can hold up a stellar remnant against gravity. The bright primary becomes a future remnant in waiting. The system becomes not just a thing in the sky, but an archive of stellar life cycles of observational correction, of cultural continuity, of the long human habit of mistaking visibility for understanding. That is not ordinary. It only feels ordinary because Sirius has been sitting in plain sight for so long. The achievement is real. Familiarity makes the star accessible. Children can find it. Casual observers can notice it. Entire civilizations can build stories around it without instrumentation. But the cost is larger. Accessibility creates a false floor under curiosity. People stop at the first rung because the object seems already handled. Bright, famous, named, done. Sirius is one of the clearest examples of how the obvious can become a mask. The more recognizable a thing is, the easier it becomes to underestimate its hidden depth. And astronomy, more than most sciences, lives inside that paradox. The heavens are full of objects people have seen forever and misunderstood for almost as long. The visible sky encourages confidence because it is available to everyone. Yet the physical truth of the sky is almost never available at first glance. Sirius should have taught that lesson decisively. In some ways, it has. In others, it keeps being reabsorbed into simplification because the eye cannot help preferring the immediate story. This is why familiarity must be treated as a liability as well as a privilege. Knowing where Sirius is does not mean knowing what Sirius is. Knowing its traditional names does not mean grasping its structure. Even knowing that it has a white dwarf companion can become another static fact unless it is fully felt as a convergence of evolutionary time-collapsed matter and observer-dependent brightness. The star is close enough to feel intimate, and that intimacy is misleading. It tempts human beings to shrink it to mnemonic size. But Sirius is not mnemonic in its actual nature. It is violent history compressed into apparent calm. It is one currently living star beside the hardened remains of another. It is a reminder that the brightest light in the sky can carry a corpse in orbit and still look uncomplicated from the ground. That line matters because it captures the entire hidden structure of familiarity. The obvious thing is often obvious only because the mind has stopped tracking what it would mean if taken seriously. Sirius, taken seriously, is not a star most people know. It is a system most people think they know, and that distinction opens the next deeper layer. Because once familiarity is stripped away, Sirius stops looking like merely a famous nearby system and starts looking like something more severe, a local demonstration that beauty, order, and brilliance are inseparable from mortality, compression, and irreversible change on a cosmic scale. The deepest lesson in Sirius is not about brightness at all. It is about mortality made visible. Most people look up and see a fixed star. Astronomy sees a system in transition, a system that compresses immense stretches of stellar time into one nearby arrangement that the human eye mistakes for permanence. That is why Sirius grows more unsettling the more clearly it is understood. Its beauty is real, its order is real, its brilliance is real. But none of those things are stable in the way human perception wants them to be. Beneath the calm of a familiar winter star lies the record of one stellar life already spent, and another still moving toward the same broad end. The story on the surface is elegant. The story underneath is terminal. Sirius A shines with present tense authority, hot, luminous, and seemingly secure. Sirius B circles beside it as the remnant of a star that has already crossed the boundary between stellar life and stellar aftermath. Taken together, they form one of the clearest nearby demonstrations that radiance and ruin are not opposites in the universe. They are phases. That is the hidden truth the system keeps forcing into view. Human beings are drawn to stars because stars seem to offer the opposite of ordinary life. They appear beyond decay, beyond injury, beyond time, as it is lived on Earth. A mountain erodes. A city collapses. A human life ends. The stars remain. Sirius has helped sustain that feeling for thousands of years because it is so recurrent, so dominant, and so visually untroubled. It rises when expected, It commands attention without visible strain. It seems immune to the vocabulary of exhaustion. But this only looks true from a distance. The real problem is scale. Stellar change is not absent. It is merely slow relative to human memory and fast relative to cosmic permanence. And Sirius is one of the rare systems where that truth is no longer abstract. The evidence is in orbit. One member still burns in the standard way. The other is the compact remnant of a completed collapse into white dwarf form. The universe has already written the later chapter beside the present one. That makes Sirius different from a merely bright star. It makes it interpretive. It teaches by juxtaposition. It takes the comforting illusion of celestial endurance and places a correction directly beside it. The brighter star does not cancel the dead one. The dead one explains the brighter one. Sirius B is not an incidental companion. It is the system's hardest sentence. It says that what looks most complete can already contain its own future in neighboring form. It says that stellar life is a temporary balance between gravity and pressure, not a permanent identity. It says that what dominates the sky now may later contract into something tiny, dense and almost unrecognizable without ceasing to be real. That is where the system's meaning expands beyond astrophysics into something larger. The obvious explanation is that Sirius is an interesting local binary. The deeper explanation is that it is a nearby proof that the universe builds magnificence out of unstable arrangements. Stars do not endure because they are invulnerable. They endure because the struggle between collapse and support can last an extraordinarily long time before one side finally changes the terms. In Sirius, both sides of that logic are already on display. Sirius A represents the phase in which outward pressure still wins, in the ordinary way maintaining a luminous star against inward gravity. Sirius B represents the phase in which ordinary stellar life has ended, and a different rule, electron degeneracy pressure, has taken over to prevent deeper collapse. Two forms of resistance, two stages of consequence, two answers to the same gravitational demand. This is why Sirius is not merely beautiful. It is structured beauty under threat, beauty already entangled with aftermath. That matters because it corrects one of the oldest emotional habits in human encounters with the sky. People often treat visible regularity as evidence of cosmic serenity. But serenity is not the right word. Stability in astronomy is frequently a managed condition, a balance maintained under severe constraints. The achievement is real. A star can shine for hundreds of millions or billions of years. But the cost is larger. The star is spending itself the entire time. Sirius makes that cost unusually legible because the system places expenditure and remainder in the same frame. One member is still spending, the other is what remains after spending. In that sense, Sirius is almost a complete argument about stellar life, condensed into one nearby case. Formation is not visible directly, but the consequences of evolution are. Main sequence brilliance is visible. Post-main sequence aftermath is visible. The relationship between mass and lifespan is visible in reconstructed form. The dependence of apparent brightness on perspective is visible. The difference between cultural meaning and physical mechanism is visible. Very few stars carry so many layers without disappearing into abstraction. Sirius does not disappear because it is too bright to ignore. That is the system's strange generosity. It delivers one of the hardest truths in astronomy through one of the easiest objects to find. And that truth is not merely that stars die. It is that what human beings call greatness in the sky is inseparable from limit, from compression, from the irreversible logic of time acting on matter at scales beyond ordinary thought. Sirius is therefore not just a lesson in what a star is. It is a lesson in what splendor costs. It is a reminder that the brightest thing in the night can already be sharing its orbit with the evidence that brightness ends. And once that is fully understood, the final reframing becomes unavoidable. Sirius is no longer just a local system, or a mythic star, or a brilliant object with unusual physics. It becomes a compact image of the larger universe itself, beautiful, lawful, violent, temporary, and far stranger than its familiarity ever suggests. The brightest star in the night sky turns out not to be a triumph of simplicity, but a trap laid by familiarity. That is the final reversal. Sirius first appears to human beings as certainty itself, a point so commanding, so recurrent, and so visually undeniable that it seems to explain its own importance. Ancient civilizations fold it into calendars, warnings, floods, kingship, and heat, because it refuses to remain background. Modern astronomy measures its distance, its spectrum, its motion, and its mass, because it is too prominent to ignore and too nearby to leave uninterpreted. Both responses are understandable. Neither is sufficient on its own. The real meaning of Sirius only emerges when the visible star is stripped of the false innocence that brightness gives it. Because what looks like one obvious beacon becomes under pressure something much larger. A binary system where appearance and structure split apart, where a still living star circles beside the compressed remnant of one that has already died, where myth, geometry, gravity, stellar evolution, and quantum mechanics converge inside a single object known to almost every skywatching culture that has ever looked up. The story on the surface is one of brilliance. The story underneath is one of layers. Sirius is bright because Sirius A is intrinsically luminous and relatively close. But that explanation, though correct, is only the first doorway. Beyond it lies the older human layer, where recurrence turns into ritual and visibility turns into civilizational time. Beyond that lies the scientific correction, where distance and spectrum separate what the eye sees from what the system is. Beyond that lies motion and the discovery that the star everyone thinks they understand is being pulled by something they cannot see. Beyond that lies the white dwarf Sirius B, a dead star still exerting force, still radiating heat, still carrying roughly a solar mass inside a body comparable in size to Earth. Beyond that lies the quantum architecture of degenerate matter, the hidden law that prevents the remnant from collapsing further. And beyond even that lies the most difficult truth of all. Sirius is not just a star system to be described. It is a visible argument against human habits of shallow seeing. The obvious explanation is not the real one. The brightest object is not the whole object. The most familiar thing is not the most understood. This is why Sirius matters at a scale beyond its local astrophysics. It is a case study in how the universe hides depth in plain sight. Human beings often imagine revelation as something reserved for the distant, the faint, the newly discovered, the exotic. Sirius exposes the weakness in that expectation. Sometimes the deepest revelation is hanging in one of the most recognizable places in the sky. Sometimes the object seen for thousands of years is not exhausted by observation, but only slowly opened by it. Sometimes the visible point that anchors myth and memory also contains the proof that stars die, that matter can be compressed into states alien to daily intuition, that brightness depends on perspective, and that beauty in the cosmos is rarely separate from violence, cost, or limit. Sirius therefore returns us to the beginning, but with the opening idea transformed. The brightest star in the sky is not one star. It is not one story. It is not one kind of meaning. It is a living star and a dead one bound together. It is ancient symbolism and modern measurement fused in one system. It is nearness that feels intimate and distances still beyond human scale. It is radiance beside ruin. It is present brilliance beside future warning. It is a reminder that the sky does not become simpler when something becomes famous. It becomes easier to underestimate. And that may be the final lesson Sirius offers. The universe does not reserve its deepest truths for hidden corners alone. Sometimes it places them in the brightest place it can, then waits to see whether anyone will look past the light itself and into the structure beneath. Sirius is that structure made visible, not a single beacon, a layered system, not a fixed symbol, a cycle, not a familiar star, a revelation that has been waiting in plain sight all along. Sirius begins as a point of certainty and ends as a system that destroys certainty. That is why it stays with the mind. It looks like the simplest kind of thing a human being can see in the sky, bright, singular, unmistakable. Yet everything that makes Sirius powerful lies beneath that first impression. The visible brilliance is real, but it is not the truth in full. Behind it stands a deeper order, one in which distance alters meaning. Motion reveals hidden mass. Myth preserves pattern before physics explains it, and stellar beauty exists beside stellar death without contradiction. Sirius matters because it takes all of those layers and binds them into one nearby reality. What shines above Earth is not merely a famous star. It is a living demonstration that the universe is structured by forces larger and stranger than appearance allows. A bright main-sequence star burns with present-tense authority. A white dwarf companion carries the compressed remains of an earlier life. One is what power looks like while it is happening. The other is what remains when that power has already spent itself. Together, they reveal the larger truth that no star is only its light, no object is only its surface, and no familiarity is a guarantee of understanding. That is the final transformation of Sirius. It stops being a landmark and becomes a warning, a record, and a kind of cosmic mirror. It shows how easily the eye settles for the visible answer. It shows how much reality waits beneath that answer. And it shows that even the brightest thing in the night is not exempt from time, from collapse, or from the deeper laws that govern everything that shines.